document our adherence to your criteria. Select a lesson in the curriculum to see the refractive cache in action. Sector 01. Multi-model orchestration. We begin our audit with the fundamental shift in how superintelligence is routed. In the current era, most applications treat AI as a monolithic chatbot endpoint. This is thermodynamically and cognitively inefficient. We have engineered a routing hierarchy that matches inference density to task complexity in real time. How does the system determine density without adding overhead latency to the request? We use a pre-refraction intent classifier. Before a single byte is sent to the Gemini API, our client-side logic identifies the activity node. For this manifest, we utilize a 100% Gemini stack to maximize logical purity and eliminate model translation decay. However, our open-source architecture is built for total model-agnostic flexibility. We already demonstrate a hybrid design in the audio layer, allowing architects to toggle between 4 distinct TTS providers: Gemini Flash, Google Cloud, OpenAI, and local system. Our platform is PWA-enabled for home screen deployment. While currently cloud-orchestrated, the architecture is prepared for the next refraction, migrating high-frequency logic to on-device local models to achieve zero-latency physicality for humanoid hardware, as discussed in Sector 10. Welcome, Sarah. I know you have a lot of projects to evaluate today. I want to jump straight into the back-end architecture of Neural Prism, specifically addressing your innovation and execution criteria. We call it refractive caching. I'm listening. Most teams are just wrapping an OpenAI wrapper with a UI. For the innovation score, I need to see something that solves the latency and cost problem. How is refractive caching different from a standard Redis lookup? Great question. Standard caching requires an exact string match. If user A asks, "What is the capital of France?" and user B asks, "France's capital city?" a standard cache misses. Let me demonstrate live. Watch the console. Okay, I see the first request took 800 ms. That's a standard LLM call. Now you're typing the second, slightly different prompt. Exactly. Hitting enter now. Boom. 15 milliseconds response time. Whoa, that didn't hit the LLM provider? That's a massive score for viability and cost reduction. How did it match them? We convert the prompt into a vector embedding. If the cosine similarity between the new prompt and a cached prompt is above 0.95, our refraction index, we serve the cached response. We refract the query through existing knowledge. That covers efficiency. But what about data integrity? If you're caching things loosely, how do you track requests across a distributed system? I'm looking at the technical complexity rubric. That brings us to deterministic UUIDs. Usually, IDs are random, v4. We use v5 UUIDs generated from the hash of the semantic content and the model parameters. So, if I send the exact same semantic payload twice, I get the exact same ID? Precisely. It guarantees ID impotency without a database lookup. The ID is the proof of content. This allows us to deduplicate requests at the edge before they even hit our core processing cluster. Alright, you've demonstrated a significant reduction in API costs and latency, plus a stateless way to handle ID impotency. That checks the impact box heavily. Let's look at the code. Welcome, judges. Today, we aren't just reviewing code. We are looking at the cognitive architecture of the Neural Prism platform.
Welcome.
Welcome, judge. This channel is pinned for your convenience. We have used this platform to self-document our adherence to your criteria. Select a lesson in the curriculum to
Welcome. I am ready to evaluate your technical skills. Shall we start with a dynamic programming problem?
Initializing interview sequence. Optimization protocols loading. Powered by Gemini 3 Pro Reasoning Engine. Welcome, Candidate 404. Today we dismantle your reliance on nested loops. The topic is the two-pointer technique. Thank you, architect. I'm ready. I assume we're dealing with array traversal? Precisely, but efficient traversal. Consider a sorted array of integers. I demand you What is an ideal CPU? Imagine a CPU that can run multiple tasks in parallel at the exact same speed. If you have two tasks, each gets 50%